So welcome everybody. I'm delighted to welcome you to tonight's talk. My name is Pam Morell and I chair the industry committee for the Founders Company, under whose auspices this lecture series is organised. And it's one of our Whitechapel lectures, which are all around the themes of materials and materials in the world. And I'm delighted to say that our speaker this evening is Dr. Sarah Harrold, a material science graduate with a PhD and an MBA from Cranfield. She's also a chartered engineer. I think Sarah started out as in research, but a research fellow then at the Warwick Manufacturing Group. She was then the innovation lead for Innovate UK, responsible for technical delivery of the Industrial Strategy Challenge Fund, which was a £250 million fund. She's now Head of Strategy and Government Engagement at Glass Futures. She's also a director of Five, which is an incubator, an accelerator organisation, a collaboration environment for startups all around sustainable innovation. So she's a director there, and also a co-director of the Foundation Industries Sustainability Consortium, or FISC, which is really looking at all of the foundation materials, which are metals, cement, chemicals, paper, and ceramics, as well as glass, which is obviously the main topic for our discussion tonight. But obviously all of those materials are fundamental or foundational, as we might say, to the whole of the industrial strategy in the UK, and everything else that you can want is all made of materials. So Sarah's going to talk to us tonight about and really asking and perhaps answering the question. And as I've said before, some of us are from the metals sector more so. So when we're asked, is glass the world's most important material, we'd probably say no, but I'm sure Sarah is going to try to persuade us otherwise. So without further ado, we'll hand over to Sarah. Tonight's session is being recorded, so if you don't want to appear on anything, then turn your camera off. We will be muted throughout, so just be aware of, say, there is a recording going on in place. At the end of Sarah's presentation, we'll be able to take a few questions, and you can either put your hand up at the end and we'll hear you, or you can pop a question into the chat, which will be available throughout tonight's talk. So Sarah, thank you very much for agreeing to speak, first of all, and now over to you.
Thanks so much, Pam, and hopefully not too controversial a topic. I was feeling a little bit uneasy about this as a presentation title, but you'll have to go easy on me because I am a metallurgist at heart. I just work in glass now. Hopefully you can all see my slides. I'm going to keep this quite informal, but really just show you why I have a newfound love of glass, and we can have a bit of a debate afterwards. So Pam has done me a super introduction, so I don't need to give any more background to myself. So I wanted really to start by bringing you all up to speed on the history and the origins of glass. It's a material that most people take for granted, as it is all around us, but actually it has a really interesting origin story and use story, and kind of shows how it's become so prevalent all around us. So glass itself is a natural material. It appears naturally as obsidian formed by volcanoes. And all the way back into early human society, it was really valued for its sharp edges and shiny beauty. So even back then, we were starting to use it as tools for breaking down harder elements around us, and for being this object of fascination in terms of its beauty. It was only around 3,500 BCE, I'm not even sure what that is, a while ago, that we decided to discover how to make it ourselves. So we've had a huge love story between humans and glass. Glass itself is made of melted sand and additives like soda ash and limestone. So naturally occurring raw materials that we concocted together to recreate that natural substance to turn into a more malleable and processable material to use around us. But really importantly, and I will come back to this, it's the precise cooling of those ingredients that make glass what it is. So it's the same with metals. For anyone who is a metallurgist, we know the way that we cool that liquid mixture down determines huge amounts about its properties. And for glass, that's incredibly important. So the Romans started a glass blowing revolution, and they started looking at stained glass for cathedrals. And the tradition and the craft really came to a head in Venice, where we were looking at mastery of coloured glass and decorative glass. So these two functions really kind of stay core to its use cases throughout history, looking at the start of natural illuminations in firstly sacred religious buildings, but then more and more into the home, but also how we tell stories and how we show meaning through an artistic form like stained glass. By the time that we got into the Renaissance period, really Venice's Murano glassmakers were world leading, and experts from the UK were going out to Venice to really learn and hone their craft, especially when it comes to clarity and colour. I don't think you can see it off my screen, but I have a beautiful piece of Murano glass here, which kind of typifies this structure of huge amounts of intricacy and colour that goes into these artistic wares, really happening all the way back from the Renaissance period. Now, glass has properly shaped how we act as society and civilization. So it's changed the way that we design buildings and our architectural practices. It's changed the way that we see the world through lenses to improve our vision, but also into the molecular level when we look at advanced microscopes and telescopes, enabling us to see far into space. It's also changed the way that we interact with food and drink and transport medicines, so huge applications across all aspects of life. So, as I am a scientist, and I know a few of you are too, I did have to include glass, the science. Glass is an inorganic, non-metallic material. So I'll come to what that means in terms of a crystal structure, but virtually it's a liquid that's been cooled in such a way that it stays with liquid properties. It's a very special form. Generally in science, if you cast your mind back to school, we have three classical states of matter: solid, liquid, and gas. But this is a special case and almost a fourth state of matter. So although they have the mechanical rigidity and solidity of a crystal, they have a random and disordered structure of a liquid. So it is this fourth state, a state in which the molecular units are completely disordered, but there's enough cohesion between them to prove mechanical rigidity. So really, really special. So if you're used to seeing kind of atomic layouts, we start on the left with quartz, which is a naturally occurring glass, and it has this regular repeating pattern of this crystalline structure. As we've started to make glasses, we're replicating that as fused silica, where we're trapping that state, but down at a solid level. And you'll see it's not a regular repeating pattern, it's an amorphous structure. And we can tailor that structure to optimize UV transmission for optics, so how we see through and how we amplify our images. We can also see that if we start to tune that crystal structure, so looking at soda lime glass, for example, this is a synthetically produced glass. It's still got that amorphous, irregular structure, but what we're doing is we're adding other additions like soda lime, which lowers that melting temperature and eases our processing. So over time, we've kind of moved away from trying to replicate this natural state and freeze in something that's not very natural into something that's easier for us to work with and has enabled us to mass produce this product. So, what does that mean in terms of ingredients? So, the main ingredients that make up a glass, as I said, are silica, so sand, silicon dioxide, with elements of lime to make it more producible. So, as you'll see, compared to a typical Roman glass, over time we've increased that lime content to make it more processable. And we've started to add in more amounts of things like magnesia and alumina just to change up that process chemistry and give different compositions. If you're more familiar with Bakelite or cooking or laboratory glasses, these still retain their very high silica content. And instead of adding soda lime for processability, we've added in boric oxide. So that same function, but giving really high temperature stability and allowing it to be used in that higher temperature window range. For packaging, we stick to that modern soda lime. That's the standard, and that's most of the glass that you'll see around us. What else do we add? So we know glass isn't just clear, it's got some of these fantastic colours in it. So we can add iron, which gives you a brown or a green colour. We can add chromium, again, that gives it that green colour. Cobalt gives it a lovely blue tinge. And we can add selenium to do the opposite and take some of those colours out. We can add sodium sulfate for improving the refining capabilities, so giving a nice, consistent, smooth finish. Or we can add nepheline or calamite to improve its durability and wearability, especially if we've got longer life products. So a little bit of the kind of complex science on why glass is transparent. So this is something that a lot of people ask when they compare glass to metals. And although this is such a macro property, actually it translates to very, very small science down at atomic level. So again, casting your mind back to school, you may be familiar with this makeup of an atom. So each atom has its nucleus concentrated right in the center. And around that cluster of protons and neutrons, we have electrons that sit and whiz around the outside. So they sit in very specific bands called energy shells, where each electron has a very specific energy associated with where it sits around that nucleus. Now, in metals, those electrons are a little bit closer together. They're a little bit closer in energy banding. So when a photon of light comes into contact with a metal or another material, that photon is absorbed by the electron because it wants to take that energy and move itself to a higher energy electron band. Now in glass, those bands are so far apart, the energy needed is so great that the photons of light just don't have enough energy to make that happen. So instead of trying to absorb them, they just let that light pass through. So it's why glass itself is this transparent material, because photons just don't have enough to make that transition happen. Now, compared to photons of light, UV waves in comparison are much higher energy, and they do allow for that promotion of that electron into that higher energy state. So UV waves in comparison are absorbed by glass, so you don't tan when you are inside. Some of that UV is filtered out, not all of the UV. I wouldn't risk standing straight against your window on a sunny day, but a vast majority of that UV is absorbed and doesn't make it, is absorbed and therefore doesn't pass through. So how is glass made? For anyone who's familiar with steel making, this is a very similar process, and I get told off all of the time for making this analogy. But we start with some raw materials, either those ones that I've listed or recycled glass. So glass is infinitely recyclable, and we can throw broken glass into the furnace and displace out the need for that raw material. Once we have a batch that we're happy with, a set of ingredients that are measured out in the right ratios, that then is inserted into the furnace, which is a large gas-fired oven that sits at about 1600 degrees Celsius. In that bath, it all starts to mix together and melt. And there are a number of kind of flows that happen within that liquid glass to move it along the furnace and down this kind of U-bend structure that you can see here and out into downstream processing. And this is where we start to decide what kind of product we are looking for out of our glass. Are we looking for a flat glass or are we looking for a shaped glass? So things like windscreens and windows are all flat glass products, and they will go down onto either a rolled plate line, so very much like steel making. They will pass through a mangle, a set of rolls, and then into downstream processing, or they will lie on a bath of liquid metal where they sit and spread out and form this lovely, beautiful flat sheet of glass. Either way, they will move down that processing line and have a very, very precisely controlled cooling, so they reduce all of the internal stresses within that glass and don't produce something that's likely to shatter at the other end. Oh, I thought I had a video about shaped glass that might be coming. Shaped glass, however, forms at the mouth of the furnace a sausage shape that's dropped down into a mold and blown out into shape. So I think that might be coming in a couple of slides' time. So just to start to convince you on why glass is this super material, not only is it around us everywhere, but actually in terms of its properties, it's super, super impressive when we compare it like for like with, say, steel. So glass is stronger than steel. In terms of its ultimate tensile strength, we can see greater than 4 gigapascals, which compared to the 2 to 3 gigapascals for steel is very impressive. Obviously, that loading has to be applied in the right way, and we do know that glass can be brittle if that load is applied in the wrong way. It's also incredibly versatile, so you can see the range of colours that we can get, the way that we can get this transparent material that's tuned to the wavelength of light, how we can get special optical properties. So the classic prism experiment, where when you hit a white light, a blend of colors at the right point in a prism, because of the tuning that happens within this crystal structure, we can get that light to separate out into its relevant colors, and you see that rainbow effect coming out of the other side. It's also incredibly durable. We can shape it and form it. And it's got impressive density control, so we can tune it to the application that we're looking for. It's also incredibly impermeable. It's very safe. It's very sterile. It can be insulating. It can be flexible if we want it to. And very importantly, it is 100% recyclable infinite numbers of times. And I don't think there are any other materials out there for which we can hand on heart say that this is the case, but I'm happy to be challenged. There we go, my glass forming video. So I'm going to, oh, it's popped out. I'm not going to do this. When I share the slides, I will share this lovely video of glass making in action, because it is very impressive. But you can see from this diagram that I included on the other side, in case, what happens in that process. So that sausage shape, that gob, is dropped into a blank mold. And firstly, we blow that bottle out to meet the outer shape of the mold. We then take that blank out and we invert it, and then we do the opposite blow so we can blow the internal shape of that bottle together. And when you get that finished bottle, that's then taken out and sent to downstream processing. This is an incredibly impressive, incredibly fast process. And bearing in mind, with some of our customers, they make 2 million bottles each day. It's an incredible feat to watch. So I do recommend this video, and I will share a link. In terms of what we make in the UK, we do have clusters of manufacturing that happen, some in the northwest, some in the northeast, and then a couple of dispersed sites across the UK. And these sites predominantly produce container glass, so manufacturing the containers for the food and drinks industry. We also have quite a large production of flat glass production that goes into windows, single, double, triple glazing units. Some of that goes for downstream processing for things like windscreens or car windows. We also have a small amount of production of fiberglass that either goes into insulation or it goes into manufacture of things like hulls for boats. In terms of statistics for the sector, there are 6,000 people directly employed and 150,000 indirectly employed in the supply chain, producing 3.5 million tons of glass each year, using quite a lot of energy, both natural gas and electricity. And we're currently recycling about 71% of our container glass in 2019. Those numbers have moved on slightly, but they're the best source that we have available. So, where is that glass going? I've already done a few spoilers as I went through, but glass is absolutely everywhere around us. In some applications that you might associate with glass, and in some that you really wouldn't. So, to start off, thinking about when we're transporting people and goods, there is waste glass that goes into road surfaces for increasing the friction and the wearability of road surfaces. Obviously, glass fibre is used in the production of boat hulls and a number of light-weighted vehicles. We've got the windows and the windscreens in trains and taxis and cars. We use it to harness the power of the sun and wind. So solar cells, huge amounts of glass go into them, and glass fibres that go into the wind turbines that you see around us on and offshore. We also use it to insulate our homes with glass fibres going into the insulation that you see in our lofts and in our walls. We use it as a sustainable way of transporting food and drink. It's integral to connecting the world. So the fibre optics that help translate that internet to your houses, the smartphones and the computers that you're watching this from, all have huge amounts of glass in their components that allow us to interact with the digital medium. Glass is often an invisible innovation, so glass flakes are applied into a number of paints and nail varnishes that give it that really glossy and shiny finish that we have known to love in certain types of paints. And just to trick you, I guess, the one image on this slide that doesn't contain glass is often your spectacles. The vast majority of our modern day spectacles are actually plastic lenses rather than glass, but you do still get some traditional sources that do use glass. So I've mentioned kind of glass in its everyday use, but obviously there is still a huge amount of glass that has that other use case in the arts. So glass has long been a preferred artistic medium as it allows artists to work with light, to capture glows, to use refraction, that bending of light and splitting out of colours, or to use distortion where when you look through something, it's like looking through water and you're seeing a very different image. Techniques include glass blowing, as you may have seen, glass casting, very much like metal casting, or engraving into a surface, or stained glass, where we're looking at building up components from huge amounts of different pieces of glass of different colours and using it to form that mosaic. We've got some hugely iconic global artists who have come through the Art Nouveau movement and really kind of redesigned these beautiful buildings and structures, through to Venetian mastery and the colours and the intricacy that comes out of these extruded and pulled glass blowing activities, through to huge, large-scale organic forms that come together in galleries of really impressive structural designs. If you have Netflix, you may have seen Blown Away, which has been released as a program over the last few years and has massively improved and increased the following that this now has as an artistic medium. So I would recommend it if you haven't watched it. Very much dramatizes the art, but very impressive what you see these glass artists achieving over a day in the hot shot. So a little bit about sustainability and the work that we're doing at Glass Futures, as I have to give a nod to my employer. So I've kind of alluded to it as we go along, but as with all of the materials industries, glass is coming under threat for a number of reasons. The first one is that we do emit a lot of emissions when producing these materials, as it's a hugely energy intensive process. And rising and important environmental regulations are having an impact on the way that processing happens. This is being compounded by escalating energy costs that have increased kind of 5 or 6 times in the last year. And when you have cost competitive pressure already coming in from alternative materials, it really does make operating very difficult. That's compounded by global supply chain disruptions, and it means that year on year, UK production of both flat glass and shaped glass is shrinking. That competitive pressure, as we might debate later on, comes from other packaging forms in the main. So if you are used to drinking a 330 ml bottle of beer, you may have seen more and more brands moving to aluminium cans as an alternative. But manufacturers are also now looking to paper-based products as well as an alternative and moving away from that traditional glass product. So we are seeing quite a lot of that coming in. In windows, not so much. No one's developed a really innovative new material that still allows you to see out and have heat kept in as well. So that one's a little bit more immune. So that glass manufacturing process, if we break it up, 24% of the emissions from production come with the primary electricity production associated with that electricity usage on site. 18% of the emissions come from the raw materials itself. So as we're breaking down those oxides into the final material, we are giving off quite a lot of CO2, and that's kind of an integral chemical process. But by far the largest amount of emissions come from the combustion of fossil fuels. So most of these furnaces use natural gas as that burner medium, and that does increase the emissions of that furnace process. So what we see as an organisation, I'll come to kind of what we do in a second, as the real decarbonisation levers, especially around, this is a specific use case for packaging glass, is we see a number of different interventions, from either reusing the products that we make, so refilling them and reusing them for a second cycle, through to our ability to lightweight their design. So like in automotive and aerospace, where there are drivers to lightweight the products for efficiency, with huge amounts of the downstream emissions for bottles coming through transport, anything that we can do to lightweight does massively reduce those emissions. Those two, however, have kind of competing agendas, whereby the more that we lightweight a bottle, the more fragile it becomes and the less likely that we could reuse it. So we really have to think about that interplay and see what we can do to make these materials more strong, or apply coatings to really optimize the way that they perform. We can then look at the processing itself, so we can increase the percentage of recycled content in that material. So once glass has been melted and formed, the energy that's needed to melt it is massively reduced compared to looking at putting that virgin material back in. So the more that we can do to capture that glass and to reprocess it and use it again, the better. We can look at low carbon fuels, so taking out that natural gas source for a number of other alternatives, be it electricity or be it hydrogen, and looking at how those perform in a furnace. And we can also use, I guess, more drastic solutions, where we can use different waste streams from different industrial processes and use them to displace out that reliance upon silica sand. So in terms of where that kind of spreads across the process, that's all the way up from the batch preparation and the emissions that go on there, all the way through, with a huge focus on that melting and refining stage. So lots of things that we can do, different furnace types, different ways of operating to optimize what goes on there, to more efficient control of that process further downstream, optimizing the way that we do things, and thinking about how we schedule and make the most of the heat that we've used in the upstream and minimize the heat that we use in the downstream. So huge amounts of information there, but really what I'm saying is there's quite a lot that we can play with. There's been quite a lot of work done through the 80s and 90s to get that low-hanging fruit, especially as the cost of energy has increased, but there's still quite a lot to go at. So that's where Glass Futures come in. So we are a brand new research organisation based in St Helens between Liverpool and Manchester, in the shadow of NSG Pilkington, which is where the float glass process was invented. And we were set up by the industry, for the industry, with a £60 million investment from the government, where we can help be that industrial testbed for how these industrial processes don't just operate in the way that they always have done. We know that long history and long legacy with where this material has come from, but actually in a way that's sustainable, uses best available technology, and also drives that technology into the future. So we envisage this future where materials are designed with reuse and recycling in mind. Digital technology unlocks new heights in product performance, transparency, and sustainability. And it's our mission to use our global innovation platform to bring together partners from industry, from academia, and from government to really turn all of this ambition into collective action. We do this through having industrial scale solutions. So we have the world's first 30-ton per day multi-fuel hybrid glass furnace. So that allows us to demonstrate all of this huge portfolio of sustainability solutions in an environment that looks and feels to an operator exactly like their own glass manufacturing facility. On site, we also have a ceramic setup. So we have a pilot scale hydrogen kiln, allowing us to demonstrate the production of a whole array of ceramics products within that environment. So we have fired bricks, we've fired plates, we've fired toilets, and shown what's possible within hydrogen as a burner fuel rather than natural gas. We have the ability to produce flat glass and shaped glass, so looking at new innovations in windows and in packaging. We have a combustion testbed, so looking at burner science and how we optimize that, as well as an end-to-end digital platform to give all of that data behind everything that we do to allow manufacturers to really understand exactly what's going on and translate that back into their own sites. So we were created back in 2012 with a vision to address an urgent industry need all around how we optimize production and secure their future in the UK. More and more members joined that mission through 2013 to 2018, and we started to take on our first funded projects in 2019. That's when the business case for the Centre of Excellence was originally written, and in 2020 that was signed off. So through 2021, 22, 23, alongside building this £60 million centre, we've also begun a programme of work direct with industry to start to explore what some of these solutions might look like and deploy them straight at their sites. So fast forward to this year in 2025, in June, we had a visit from the Prime Minister, and very shortly after, we lit our world's first low carbon furnace, and we started delivering openly accessible, commercially available, multidisciplinary glass trials within our facility, with huge amounts of translated learning around heat recovery technology and process optimization that translates across all of those foundation industries. Just to, hopefully this one, is embedded, show you the scale of what we're talking about here. This is a huge industrial facility. You can see the Saints Stadium there for scale, where we have everything back from our abatement plant, so very much process emissions control, as you'd expect to see out in industry, that takes us through into our 30-ton per day furnace setup. Every component that you would expect to see in an industrial manufacturing plant is here just about a third of the scale. So you can see here, you wouldn't do this now, but a view inside of our furnace where you have burner ports on the side where those gas-fired burners come in. And in the bottom half is where that liquid bath sits with 80 tons of glass that sits in there at any one time. 30 tons per day is pulled out of that exhaust hole down at the bottom to the right, that then moves out into this downstream processing. So this is our flat glass line that rolls out down this roller system. And then on the left-hand side, you'll see where our shaped glass line has now come into play. On the other side, it speeds up and it makes you feel a bit sick, so apologies for that. But just a glimpse of our batch plant where all of these raw materials are stored and weighed out onto that conveyor belt system before they enter the furnace. So just a whistle-stop tour of the Glass Futures facility, but hopefully we can host an industrial visit maybe next year. You don't need to see that again. So what does the future hold? We are exploring all of those areas of sustainability and process and product optimization that I mentioned. So some of that is in process efficiency, looking at these new future fuels. So how does hydrogen or biofuels or electrification work in these furnaces? And what does that mean for product quality and products of the future? How can we use best practice in digital innovations to mean that we have all of the data interconnected? So when you look at your bottle of wine that's appeared in front of you, you know exactly what raw materials have gone in, what processing history it's had, how and where to recycle it, and the manufacturers know exactly what's coming back to them and when. How do we look to the circular economy? So we know that by recycling, we reduce the amount of energy that's needed to process these materials. We stop material going to landfill. It's just the right thing to do. But actually, in terms of the systems that are needed to enact this change, it's a very complex setup that's needed, because as soon as glass gets broken down and colours mix together, it stops us from being able to use it. So how can we think about how to best collect this material and get it back in for the manufacturers? We're also looking at more advanced materials. So as I said, this trade-off between lightweighting and performance, how do we think about what coatings could be applied to make those bottles stronger and last longer and allow us to do these refill cycles? How can we look at embedding digital technologies? So as you're driving your electric vehicle, your sunroof acts as a battery and generates solar energy for you to recharge your car. So huge amounts of opportunities there. We're also a huge skills hub. So we are equipping the industry with all of the skills and knowledge that we develop and help give a sustainable future for this industry worldwide, not just within the UK. We're training on currently available technology, emerging technologies, new processes, everything that sits around. As we're building this collaborative ecosystem between academia and researchers, manufacturers of glass, but huge amounts of brands and other end users who have an impact in the design and the use of these systems. So you may see some familiar names here across our membership. Diageo, huge manufacturer of food and drink, Molson Coors, Heineken, as well as manufacturers of shaped glass products like Encirc, flat glass like Guardian, medical glass for vials with Cena Medical, as well as a number of kind of enabling partners as well. So just to wrap up in terms of the future of glass, I hope I've made a compelling case that glass is a wonder material. In terms of where that might take us, we are looking at smart glasses, so glass that adapts to light and temperature and gives us dynamic control. That might help on a day like today where it's absolutely freezing and we might want to let more of that light through. But more and more in greenhouses, actually you want to tailor the different wavelengths of light that are coming in to help us grow different crops or to optimize those growing cycles. So a glass that allows you to do that from day one can be really, really important. We're looking at flexible designs. So how can we produce bendable and ultra thin displays that allow you to roll up your phone and put it in your pocket rather than kind of the big bulky things that we've got today? How we can look at transparent solar cells so we can build buildings or cars that generate their own power. How we can look beyond Earth and how actually we can start to produce glass out in space and building these new ecosystems. Or how we can just extend our ambitions in the architectural space. So you may see some of the ambitions that happen across these new developments being dreamt up in Saudi Arabia. So how could we do a full glass bridge without the need for steel and concrete reinforcements? Or how can we do a mass facade of a building without needing to break that up into panels? So all of these kind of innovations coming through. So, is glass the ultimate material? Well, it's ancient, yes, yet it's futuristic. It's functional, but beautiful and sustainable. It enables global communication and us to be talking this evening. It's infinitely recyclable, especially versatile. We can stand on it at heights that we never thought we would achieve out in Canada. But if you're still not convinced that glass is the ultimate material, to end on a little bit of science, because glass is this fourth state, we can actually create metallic glasses. So if you cool down your metal in a super complex way, we can prevent it from having its regular, repeatable crystal structure and actually give it no crystal structure at all. So it becomes this amorphous material with the strength of metal, but the flexibility of a glass product. So it's already in development. There are a few test cases out there globally, but where metal and glass come together, we could have an exceptional mechanical performance of ultra strong but high elasticity and scratch resistant properties with unique combinations of magnetic and electronic properties that's lightweight and corrosion resistance. At the moment, it's being dreamt up for sports applications, medical tools, aerospace, and robotics. But who knows as this becomes more mainstream where it could end up. So, if you are a metallurgist at heart, maybe in the future you will love glass too. So, thank you very much. Any questions?
Thank you, Sarah. I think that's yes, you've made quite a compelling case there. I think for for glass. I think we did have a few questions that have come into the chat, and I was also, I mean, it sounds like clearly, like all the foundation industries, glass, like our foundry industry, metal sector, you know, the economic and net zero challenges are pretty enormous at the moment, aren't they? Yeah. It's impressive what Glass Futures are doing in terms of addressing all this. You mentioned you've been looking at hydrogen as a fuel. We've seen a lot of discussion around this. It still seems to be there's a certain amount of skepticism. I mean, we were thinking originally it was going to be almost like a direct, not a quite direct swap for natural gas. But obviously there are some issues. It's a lot smaller molecules. There's some, you know, embrittlement issues. There's the transport, all that sort of thing. I mean, do you think it has got a future, perhaps for more big industrial sites that are on gas networks or where gas will be delivered, or hydrogen gas, I mean, or, you know, rather than say in a sort of foundry environment? Because we've certainly heard from, you know, from melting furnaces for our sector that possibly hydrogen isn't that, you know, isn't that realistic. I just wondered if you had a sense on whether we should be positive about hydrogen.
A very good question. So from a scientific point of view, if you use electricity to produce hydrogen, you have got an automatic loss of energy that goes through that process because it's a secondary production process that happens. So logic dictates if you could use electricity, why would you not use electricity? And I very much believe in that statement. The challenge for glass is we have optimized our production process to be these kind of big swimming pool arrays. So if you imagine a kind of 25-meter swimming pool that have a number of electrodes in the bottom that are heating that glass, you will always have this massive solid surface that has a huge tendency to solidify itself. So once glass solidifies, it's very hard to undo that process. So at the moment, we do need some kind of a top-fired balance to an electrified furnace to prevent that from happening. Whilst it isn't the best vector, hydrogen is the most sustainable alternative if you don't want to use natural gas or biofuels. But it's definitely our ambition to look at what the options are to move to more disruptive technologies that could take out the need for that top fire. So things like radiant heat from the crown. How could we increase the amount of, say, electricity that we pass through the refractories to give more radiant heat? How could we look at Mark Jolly's famous plasma technology to change the way that we look at burners? So it's definitely on that kind of early TRL journey to explore. But at the moment, it has been accepted by the Climate Change Committee that the natural top-up vector at the moment is hydrogen. That's more realistic for some sites like our partners at NSERC that sit on the HyNet development up in Chester, compared to, say, sites over in Sheffield where you'd have to get off-site hydrogen brought in and the economics then really don't stack up. So it will be site dependent, but at the moment it's the only technology that we've got that could get us to net zero production.
Yeah, okay. So it's clear electrification is still the main thing that we're driving for. It's just there's other barriers in the UK to take that. I think we had I think Simon, if you're listening, you had a Master Simon had a question about deposit return schemes. I think
Yeah,
Simon, I don't know if you want to unmute
yeah.
and jump in.
But I have two things. Sarah, I notice you're a freeman of the company. Congratulations. That wasn't mentioned in your
I
introduction.
should have mentioned that. I've got it on
Was
my bit of paper. I forgot to mention it.
probably
Yes.
the most important thing of the lot. And behind you, you've got a freedom of the City of London. Yeah. So why aren't you a liveryman? That's question one.
Give me time. I only have a couple
Okay,
of months
you've had 50 minutes. And no, more importantly, I was at a lecture last week about plastics and things like that. And one of the points that was made in that lecture was that in Ireland, they've introduced the deposit for the bottle scheme back, and it has massively increased the amount of glass that's being recycled. And I wondered whether that's something that your organisation would be looking at, because I'm old enough to remember when we had the Corona bottles and we had to pay 10p a time and got the deposit back. And apparently in Ireland, there's a lot of bin dipping where they're going in and finding glass and where, and because here it just gets recycled or just gets thrown into landfill, as you mentioned. I just wondered if there's anything being done about that.
Yes, it's a very good question. And we are unlike quite a lot of our neighbours across Europe in not having a deposit return scheme. It's been a very topical debate over the last kind of 5 years across the industry, where the defence from DEFRA has often been that our curbside recycling rates are so good that we don't want to disrupt that habit. And especially since COVID, when more people are shopping online, less people are frequenting places like supermarkets, which would be the natural collection point for said bottles. So they decided the lesser of two evils was to stick predominantly with curbside recycling. The industry were overjoyed at this because their worry about deposit return schemes was if those bottles aren't separated at point of collection and a brown bottle gets crushed and mixed in with a green bottle, is actually counterintuitive in terms of recycling because you can't do much with either of those. But technology can be key here, and I think with better separation technologies and a mixture of curbside recycling and more frequently used locations that allow you to do a deposit return scheme, it would be good. We just need technology that translates across the two, so you could use your smartphone before putting your wine bottle in your curbside recycling and still get your deposit back, or going to the supermarket and doing the same. But we don't want to penalise those not going to the supermarket. So yeah, much of a muchness. Also questions about how much a 2p coin is worth to your grandchildren who might be the ones going and returning those bottles now. So a little bit of an economic argument about what the right incentive value should be.
Depends how much gin one drinks, I suppose. But thank you very much indeed, Sarah. It's a very, very interesting talk. I'm very grateful you did it. Thank you.
Thank you very much.
Pam, I can't see my hand up symbol.
Oh, yes. Sorry. Yes. Go in, Tom. Jump in. Yeah.
Sorry, if I can jump in, please. First of all, thank you, Sarah. That was really illuminating and interesting. And I probably, and from a physics and a chemical and a metallurgy style science background, is really, really all very helpful and very informative. But if I can go to be more commercial, which may not be probably fair on you, I know Pilkington has been absorbed by Nippon sheet glass company many years ago now, and I'm just interested that it's still the nub of where you are, where things are happening tends to be in the northwest region there where Pilkington originated from. And if I dare ask, the 60 million pounds that was put into trying to sort out what we might do in the future and so on, who put the money into that? Was Nippon involved in that, or was
so? NSG were a supporter at the time and are one of our members, but the funding itself was committed as a joint investment between Liverpool City Region and their combined authority, St Helens as a council, and Innovate UK on behalf of what was BEIS at the time. So it was a three-way investment.
Well, brilliant, excellent answer. And so my next question is, given that we're all being punished to death for using large amounts of energy, and this includes the metals sector, in your perception, do you think this industry's got a chance to survive? In the United Kingdom particularly, because we've got the same issues in the foundry industry. What's your take on where we are in that regard?
Yeah, I think it's a very interesting question, especially being a steelmaker by background. I think we can't always do what we have done and assume that we can commercially sustain ourselves in the UK. I think we've got to differentiate ourselves against markets where we can't compete. And so producing low value, mass produced goods, unless there are controls around imports, is probably not the way that we are going to be viable. So personally, I would look at reshoring automotive glass production, where actually that is a high value product. And because it's higher value, we can afford to import it from Germany. So we've started to do so rather than making it ourselves. I think we should look to close the loop on our glass packaging systems. So NSERC, for example, have developed a 360 model where they receive large vats of wine from Australia, they make the bottles, they fill the bottles, and they send them out to the UK market. If they then take those bottles back at end of life, wash them and refill them, we've got a very sustainable local model. So I think we do need to pivot our business models and how we go about this, how we think about higher value applications, coatings, more functional materials. I don't think we can compete in mass commodity products.
Yeah, well, that's actually exactly mirrors where we are with the foundry industry, sadly. But nevertheless, that's great. Really appreciate your help. Actually, please become a liveryman ASAP. We would do it.
I'm trying.
Very good. Thank you, Sarah.
Thank you.
Bit of a process to go through, isn't it? But you'll get there. I think the freedom is the next stage, obviously, and then it's fairly straightforward.
You haven't got the eagle eye.
Exactly, yeah, exactly. So that's once you've got that, then I think that's then it should be fairly straightforward. But yeah, I think it's going back to those. The fact the metal sector. We've got a lot of unlike steel, say, and I don't know whether it's the same with glass, but we're not. We have a lot of small companies as well, and a lot of value added. So we're often not classed as energy intense to get some of the benefits, which is another challenge. I guess it's the same for the well, it may be different for the glass industry. Maybe you've got more big companies. Yeah, I can see we've got a question from Phil as well. Do you want to jump in, Phil? Thank you.
Hi there. Thanks, Pam. Sarah, fantastic talk. Thank you. Your new facility at Glass Futures looks incredible. And I was just wondering how much of the kit that you've got in there was already commercially available and you're just putting it in there to kind of share best practice, and how much of it do you actually have to sort of develop for the purpose? Things like your hydrogen kilns, is that just the first one in the UK, but it was available elsewhere, or have you actually had to develop that?
So, very good question. We are the first and only 30-ton per day production facility. So we have scaled down currently available technology. So in theory, everything that we have done is innovative because no one sits at this in-between stage. But we are the only hybrid furnace. So I don't think any operators would increase the number of options that they have in terms of fuels like we have. We are a test case. So completely brand spanking new in that respect, but probably not what industry would then go on to do. We've tried to build innovation into everything that we've done. So our downstream lines, we've built them to be modular, so we can scale production from 1 unit up to 8 units, depending on the capacity or the types of trials that we're doing. So I wouldn't say any single component is off the shelf, either because we've had to scale it down or because we've done something innovative in its nature, but we've worked with current suppliers who wanted to demonstrate their next available technology in an application that could take a higher risk profile. So commissioning has been challenging, but definitely worth it in terms of what we're demonstrating for the global industry.
Fantastic, thanks.
Thank you, Sarah. Yeah, and I think sort of touching back on some of your other hats, thinking about those foundation industries more generally. I'm sure you're going to say yes, but do you think there are things that that we as metals and particularly as foundries can learn from what you're doing in glass?
I would say undoubtedly so. I think especially in the way that we are bringing these digital models together, we're learning about, we may have thought that all of the low-hanging fruit when it comes to process optimization and energy efficiency is being captured, but actually, are we? Are we still over engineering? So how can we look at continuous processes, batch processes, minimizing the waste heat that we're losing, but also looking at a more systems level as to what we can co-locate on industrial energy intensive sites. So we're thinking about how we capture our waste heat, how we use it to power supplementary processes. So we've got a tenant on site that uses our waste heat to power their carbon nanotube production process. So a high value on-site application that, if they pay rent to us, reduces the operational costs of a facility like ours. So I think in that respect, it may not be in the precise processes, but actually a lot of the toolkits that we're developing and a lot of those kind of holistic wraparound technologies, I think there's a huge amount that we can come together and share best practice on.
Great. Okay, that's I thought you probably would say something like that, but it's positive to hear it confirmed. I think from our sector, we've got a project with you already, and the Royce Institute. I can see Richard's got a question as well, so I'll come to him in a second. But we've got a project looking at use of waste foundry sand or spent foundry sand. It's a byproduct effectively, and we're looking at whether it could be used in glass, which is obviously one of the things. But I think also we've got a net zero panel looking at all aspects to do with sustainability and energy, and it might be worth, I would suggest, possibly a visit up there, and obviously other people can come along as well. We could open it up and maybe have a sort of bit of a works visit, as you say, which would be quite useful. So Richard, I'll come to you quickly. We've only got a couple of minutes left, but if you want to jump in, Richard, CMF.
Yes, really fascinating presentation, and lots that we could learn in the metal sector from what's been talked about tonight. I just wondered how you saw the glass industry facing the challenges of trying to persuade government and the regulators to change regulations and permitting to get toward a more circular economy, as opposed to the linear economy we've got at the moment when it comes to recycling and sustainability.
Yes, a very, very good question. And part of the reason why sites like ours were set up, so we can have some of those permits in place, so we can accelerate the kind of innovation journeys and at least pilot things a little bit more quickly. And I guess we are at a slightly better standpoint, maybe in our industry, where we already treat cullet as a material feedstock. So it's kind of exempt from some of those waste rules. So kind of on site, we've got a little bit more flexibility. But as Pam says, as we're looking to more innovative solutions, so either using spent sand from other industries, using things like ashes from biomass plants or waste to energy plants, as we're starting to take some of those things as raw materials, that's where we're struggling to get through some of these permitting and regulation trials. And especially if we're looking at food and drink applications, or absolutely in terms of pharmaceutical applications, the ability to confirm that no likely heavy metals or other potent ingredients exist within these more unpredictable feedstocks is very, very important. So kind of product standards is then holding back the innovation. So it's hard to engage with government. They don't understand. They don't necessarily listen to industry. But I think having one collective voice with very clear messaging is the best thing that we can do. And we're trying to join up across our industry. So windows and packaging aren't speaking separately, but kind of trying to join up the dots and act as a convener.
Good, yeah, good answer. There's a quick question from Alan in the chat. There's a company in the US, Met Glass, which made metallic glass transformer sheets. These were light and ideal for street transformers in the US. Does this application still go on, is the question.
Alan, I expected you to pick up on my golf clubs, but I did not know about that. So I will have to look it up and I will get back to you.
Well,
Lovely.
they started back in the 1970s. And the particular thing is that in American streets, in the sort of out in the back and beyond, electrical transmission is done in small overhead sort of cables, and for every house you need a transformer because of the 120 volt use in it. And these little and there are transformers in every street, in the States in that way. And this was actually, it was a very high boron containing iron alloy, but produced very much in the glass form. And you could produce a transformer with about a third of the weight of a normal steel one. So I was just intrigued whether that was something which had crossed your mind, because you mentioned, metallic glasses, and but can I also just ask you? Well, my dream is that every house should ultimately be like a silicon dioxide sheet on the outside of the brickwork, and would collect light, for energy. I mean, is there any moves in that sort of way?
Well, we might have our windows made of glass energy generators.
Windows, yes, but the actual whole, wall structure of houses.
Brick has other purposes in terms of insulation properties. So got to think about that. Also got to think about the availability of some of these materials and how realistic it is to coat houses in them. But I think as the technology progresses and the affordability develops, I'm sure there will be some test cases at least, because the house needs to work for us, not just be a static building. So I'm sure we will see some developments like that. And apparently this is going on in China. So I'll leave the chat to it because it's not my area of expertise. I just wanted to win you over that I wasn't a complete metal hater.
No, exactly. Well, thank you, Sarah. I think it's been a very, as we can tell from the discussion, it's prompted a lot of questions and some really good discussion there. So thank you very much for taking the time to prepare and to present to us this evening. Just to flag up to our next lecture, which will be in February. Date to be confirmed, but we're going to look at the history of something that's very close to our hearts, which is bells and bell making in the UK, which we did look at some years ago, but it's well worth a revisit, I think. So you obviously look out for that if you'd like to join us for that. And also just a quick advert for Bistro 1365, which is the lunch, very good value lunches hosted on certain days at the hall, and anyone can book a table and bring guests along to there, and you'd be helping to support the hall as well. So once again, thank you very much, Sarah, for talking to us tonight. Thank you everybody for coming along. Thank you to Eloise as well for hosting the lecture tonight for us out of hours, so to speak. And I look forward to seeing many of you either next time or at an event in London in the future.
Thank you very much, everyone.
Thank you.
Thank you. Bye bye, everybody. Good night.
Yes, thank you.
Good night. Bye bye. Bye bye.